Thanks, Leslie. Uh, Welcome to the Cohere Labs Computer Vision community. Here we are focused on exploring the unknown together. Cohere Labs is a hybrid research lab and an open research community dedicated to contributing fundamental research in machine learning, working to solve some of the field's most challenging problems and creating more points of entry into the machine learning research for the newbies as well as for collaboration with the uh, folks who are experienced in this field. We have more than 3,500 community, open size community members, 130 countries that are represented, and we have more than 450 virtual events that are hosted. And yeah, at this point, we have more than 15 plus community-led programs, community-led events. And there's a road to research where we aim to spark new ideas, inspire research connections, and support one another in navigating the field of research. We are worldwide, and as you can see, there's 8 subfield groups here, but yeah, we have increased 3 more subfield groups. So at present, we have 11 or 12 right now, and more are in works. And yeah, slide about Boyi. Boyi is a research scientist at the NVIDIA Autonomous Vehicle Research Group and a postdoctoral student at the UC Berkeley, advised by Professors Jitendra Malik and Trevor Darrell. She earned her PhD at the Cornell University. Her research focuses on embodied intelligence, leveraging multimodal data to develop algorithms and systems with key areas including reasoning, large language models, generative models, and robotics. She emphasizes aligning representations across 2D, 3D, language, and audio data. Yeah. So this is all from me. Boyi, you can take up the stage here.
Okay. Let me share the screen.
Yeah, we can see your screen right now.
Okay. Yeah. Thank you for the invitation. Hi everyone, I'm Boyi Li. Today it's my great honor to have a presentation here. Today I will talk about scaling vision pre-training to 4K resolution. In today's talk, we'll be divided into 3 parts. For the first part, I will explain the motivation behind this work, which is why do we want to scale up the resolution for vision models? Because in the recent few years, people have mainly focused on scaling other dimensions of vision pre-training, such as model size, data size, etc. But very few research really push the limit of the input resolution. And I would like to explain why this matters just as much, if not more, than scaling along other dimensions such as model size. And for the second part, I will introduce how to scale up vision pre-training to ultra-high resolution. And finally, I will talk about some limitations of the current models and some exciting directions to explore in the future. So first, I will explain why do we want to scale up the resolution, why it's important. Obviously, it's better if your model can process larger images. But the reason we ask this question instead of scaling up input resolution, because people have been focused on scaling up vision pre-training along several other dimensions. For example, people have tried scaling up the data. In the past decades, we move from small datasets like CIFAR10 to million-scale datasets like ImageNet, which we've been seeing using for many years. And then we scale it up to the billion-scale datasets we have now. People have also scaled up the training compute. So for example, you could see it's expressed in GPT hours, the cost of a single training run ranges from 4 to 40,000 GPU hours on the A100 cluster we used for development. And people have tried scaling up the model to larger sizes. For example, in intern VL, they tried a vision encoder with 6B parameters, and there was effort from Google that scales up VIT to 20B parameters. So, are these the best ways to scale up vision pre-training? And from the past experiences, we see scaling up data and compute generally works. More data usually makes it better and more robust. And given enough data, training for longer can also make it better. However, we are not so sure if scaling up the model size is really necessary. One evidence is that even in the state-of-art MLMs like Gemma 2 or Q1VL, the vision encoders are still around hundreds of million parameters, and we didn't really need to see a much difference when we scale up the vision models to, for example, billions of parameters. But for language model, we do such an advantage. So in a previous paper called When Do We Not Need Larger Vision Models, we studied if there is better ways of scaling up vision models. And we found that scaling up the size of the input images is more important than scaling up the size of the model. Our approach, called S2, is really simple. Training-free way to scale any vision models to larger image scales. Here is what we did. For a larger image, we split it into small tiles that can fit in the model. Process each tiles and put the back together as the feature map at a larger image scale. We also concatenate this feature map with the original feature map to get the multi-scale features. Specifically, we found using larger images gives better performance than larger models in lots of downstream vision tasks. What's even more interesting, we also found the representations learned by using larger models can also be learned by using a small model but larger input images. This means whether for the purpose of getting better performance or learning richer representation, larger models are probably not necessary, and the larger images is what you need. Before I dive into specific findings, I would like to briefly talk about how we scaled up to larger images here. And even with this simple method, we still see scaling up images scales works better for scaling up model sizes in lots of downstreams. For example, in this figure, we could notice that, like by scale up the image scales, which is this is the giant means the model size, and also here is a scaling on the scale, which is on the scale on the image sizes. And this line, the dot line, shows we scale on the model size. We could see scale on the model size can bring us benefit, but scaling on image sizes actually can bring more benefit, so which is higher than scaling on the model size. And this circle, the sense of circle means how large the input image it is. So this means that actually we could see more benefit from scaling up the input image sizes than scaling up the model size. What's more interesting, we also found smaller models with larger images can learn similar representations as larger models. How we verify this is we try to reconstruct the features of larger models from either a base model with larger images or from a giant model. Theoretically, all the meaningful representations in the larger model should be able to be reconstructed by the giant model. And we calculate if using a base model but larger images can achieve a similar reconstruction quality. If it does, then it means those representations in the larger model can also be learned by a smaller model but larger images as well. And it turns out the base model usually can perfectly reconstruct the features in larger model. We tried this for different region backbones, such as VIT pre-trained on ImageNet, MAE, and also OpenCLE. And we found a similar trend. This means by using larger images, we can also learn just as rich representations. To summarize, scaling image size can learn similar representations and usually gives better performance than using larger models. So it's time to focus on scaling up the input resolution for vision models. Therefore, today I'm very excited to share our recent work, scaling vision pre-training to 4K resolution. So for the next part, I will talk about how we scale up the pre-training resolution to the limit. And this is all the collaborators in scaling vision pre-training to 4K resolution. And this part will primarily focus on our recent paper here. Okay, so although the results looks very promising, but we do see a lot of missing parts. For example, S2 didn't scale up to very large resolution, and S2 didn't scale up resolution in pre-training. It just did the analysis. So like S2 only scales to the resolution to up to 1K and didn't go further. But if you compare with human eyes, which have an effective resolution of about 10K, we need to push it further to catch up with human vision. Second, S2 only takes an already pre-trained model and run it on larger images, but it didn't scale up the resolution during pre-training. This will lose the chance of utilizing the larger scale pre-training data to learn a high-quality, high-resolution representation. And as a result, it can limit the downstream performance. So, scaling pre-training to higher resolution sounds like an easy job, right? You just use higher resolution images, like how you scale up model size. You just use larger model. And if you want to scale up resolution, you just use larger resolution and probably more detailed captions. That's all the thing we will need to do. But although this sounds very easy, there's very, very few works about this. So why couldn't we do it before? The reason is, it's just too expensive. For example, let's take clip style pre-training as an example. It needs to process the whole image, what is at least quadratic compute. So it will be very hard to scale up to even to 1K resolution. So is there any way to get it around? We know it's expensive because the model needs to process the whole image. So what if it doesn't have to? For example, if the caption is about a small detail in the image, like the text on the boat. So we could see here is a boat and the text. Then we don't really need to scan the whole image to recognize the detail. We only need to focus on that specific region to read the text. So as long as the model knows which region the caption is talking about, it only needs to process the small local region in high resolution, and all other regions can stay in low resolution. And that will save us a lot of compute. So in this case, what we do is that we just pay attention to what we really cares about. And that's basically the high-level intuition of our model PS3, which learns high-resolution representations by contrasting between local regions and local detailed captions. And we show this can help us scale up pre-training resolution to 4K with a near constant cost. So that's the high-level intuition. If we really want to make this work, there are lots of details in the implementation. Let's jump into it. First of all, we need to redesign the data. So we need the high-resolution data, the pairs of local regions and local detailed captions. For example, this relax, and this means the red and white sailboat says relax on its body. First of all, for the data, what we definitely need is high-resolution data. It turns out lots of images in the existing datasets have naive resolutions of up to 4K. But we actually didn't use this 4K to train the model. So what we did is we sourced those images from the existing datasets, including this like data comp 1B, idle words, PDFA, and WDS. So we basically utilize 70 million images up to 4K resolution. And also, of course, metas segment anything 1B data. To achieve this, we built an annotation pipeline, which first detects the salient local regions with rich details, and then gets captions of these regions. Specifically, you can see from this image, we can guess the corresponding regions of the details. And then we do the salient region detection to detect the most important region. And then we feed that into multimodal LLM to get the corresponding annotation. So in this case, we could see, like for each region in this image, although it has many details, but we just cross the corresponding salient region and then annotate these regions. And with these high-resolution images, we need to connect pairs of local regions and the detailed captions of those regions, so we can do localized contrastive learning. So for example, this image shows the vibrant green and orange building, and this shows the motorcycle, and this shows a portion of the first image focusing on the area with the boat and the green and orange structure. And this one shows a close-up crop from the first image focusing on a section of the boat. And the second part, we will design the model. So we need to assign it the ability of knowing where to look at, also to enable its ability of extracting high-resolution features from local regions. To achieve this, we design a model that consists of 3 stages. In the first stage, it extracts no resolution. In the second stage, based on the low resolution features and some text prompt, it decides which regions are more important or more relevant. Or if there is no text prompt, the model will adjust based on its low resolution feature itself and predict which regions are more salient. And for the last stage, it takes high resolution patches from the regions with higher importance scores and run them through the same VIT to extract high resolution features. In this way, the model is able to both encode the low resolution images and selectively encode high resolution features based on any text prompt or saliency. So you could see, first of all, we do the low resolution feature extraction and to find the salient information and process them into the corresponding features. And then we do top-down and bottom-up patch selection to find the saliency. Then we feed these regions into the model. Meanwhile, we also will process the low resolution features, this 378 and 378 to the model. And the last part is algorithm. We will optimize the region selection and optimize the high resolution features. So lastly, for the algorithm, we have two objectives. One is localize the contrastive loss. So here we could see the corresponding regions with the text. And one is the point-wise binary classification loss for patch selection. So once we select these regions, we also do the patch selection, the binary classification to see if it's fit our input prompt. And then we put all these things together, and including the data connection, the training, like as a model as well as the algorithm. So PS3 can process to up to 4K resolution and encode the arbitrary high resolution regions based on image saliency or text prompt. We can also see the model can deal with different prompts and different types of images. So how we use such a model? Here we show that we can use this module as the vision encoder to build a multimodal LLM, which we use it into one of the state-of-art VLM, which called VILA. And once we replace the vision encoder with our PS3, we can build a VILA high dimension, which is VILA-HD. VILA-HD is able to process up to 4K resolution images, and in an efficient way by selecting the patches relevant to the user prompt. It can also flexibly adjust the computational cost at training or test time by deciding how many high-resolution patches to select. So here we could see, basically we utilize this procedure to do the whole thing, and then we apply it to the VILA to make sure it can work pretty well. And then we test the VILA-HD on 7 high-resolution benchmarks and observe superior scaling properties, much better than not high-resolution pre-training. So here we could see the circle shows the different methods, and the size of the circle shows the tokens that have been used for multimodal LLM. And we could see that with the same resolution and the same number of tokens, because the other model might downsample those original image, but PS3 can directly process these high resolution images. So PS3 can embrace much higher resolution. And similarly for other resolution and to 4K, we have to emphasize here that till now, only PS3 has the ability to process this high resolution and to 4K. And all other methods cannot deal with the 4K resolution because of the memory limitation. So we cannot use Boyi-A100 to train this model. So in A100, PS3 can successfully process these images and make this trainable to 4K.
Just a quick query here. So how does PS3 select the high resolution patches here?
So we just talk about it will use the saliency.
Okay, good.
Yeah. So basically, this can scale with contrast cost and can also trade more training test time compute for better performance. We also compare VILA-HD with state-of-art multimodal LLMs, and we could notice that like PS3, of course, can process to 4K, while other methods cannot. Meanwhile, PS3 this shows like how many high resolution, how many patches, the size of the patches we select, which like the size of patch is 33% of the whole image or 73% of the whole image, or like the thing. And we could notice that PS3 actually can process different resolutions very well, and it can outperform the previous methods with a very reasonable number of tokens, much less than these SOTA methods. So this is very impressive. That means, although you mentioned that tokenization is very important, but our PS3 actually doesn't need too many tokens. We just process the most important patches, and as well as the whole low resolution image, it can then give you a very good answer about it. Since PS3 improves efficiency by selecting local regions to process, and we compare it with other token selection and token reduction methods. So also they basically reduce the tokens to less. So you can see like 50%, and our PS3 can reduce it to 25% or 20%, right? And most state-of-the-art token selection methods are heuristic based. So basically, they just use a learnable things to reduce the tokens. For example, they use the attention map in large language model to select which tokens are important. So basically, they didn't care too much about the regional information. And in this way, we could notice that no matter how we compare with it, by downsample to the same number of tokens, PS3 actually can have much less latency and works better and consistently have better efficiency and performance. And we also have to mention that only PS3 can process to 4K resolution. So here we show a demo why PS3 is so important. For example, like when we have a high resolution, and the question is, where does the axis lead to? So if this is a low resolution, the image, the model may not be able to see the text there. And for example, for Q1, usually it has to downsample the images to the smaller one. But if it's downsample to smaller one, the latency might be reduced, but it will sacrifice the accuracy. Or it's didn't downsample, it's just processed to the original input size, it will have very long time to process the whole image. Therefore, we require VILA-HD, which largely reduce the latency, but also guarantee the accuracy. So here we can show like the Q1 VL, when processing every image, every frame, it requires a very like a long latency, but for Q1 VL, is still slow. It's a little bit faster, but its accuracy is very low. But our VILA-HD, we could see that it went very smoothly and the accuracy is 100%. So after seeing these very good results, many people may ask, if we really need a 4K resolution for these tasks, will it be too much? And I think they made a valid point, because if we look at the scaling curve we showed just now, we could see there's not too much performance improvement over the 4K and this 2K, this 1.5K to 4K. Therefore, we run a check on the existing benchmark, and it turns out we actually only need to pretty low resolution to solve these benchmarks, even though they contain pretty high resolution images. For example, in V-Star Bench, which contains images with low resolution between 4K and 2K to 4K, the questions are very easy to answer under 1K resolution. So for DocVQA, only 512 resolutions is enough to answer lots of questions. That means maybe it's not 4K is not necessary. It's because all the existing benchmarks are too simple to be solved with 2K or 1K resolution. For example, in V-Star Bench, here we could see it just crop that, and it can see the motorcycle, and it would just ask you, what's the color of the motorcycle? So even it's 512, we still could see the color. Or in the DocVQA, like what is the mortality rate in the year of 1940? And we could see with lower resolution, the text still clear. Therefore, we noticed that these benchmarks are not enough. So we manually connected the minimum recognizable resolution, which is the average minimum resolution, to answer for each benchmark. And we found most benchmarks can be solved with under 1K resolution. So you can see here. And this explains why we did not see much improvement when we scaling to 4K resolution. Therefore, we also, you can see, connect the data set ourselves, which is called 4K Pro. That like we must need 4K resolutions to process this task. And we also open releases on the website. So please feel free to check it and use it in your experiments. And here we show how we need a 4K resolution in the real world. In fact, it's still necessary in lots of scenarios. For example, when you are driving and when you need to figure out which exit to leave, or when you are using your laptop to or playing games. So you need to understand what is the text and how it looks like. And this motivates us to build a benchmark that reflects the necessity of 4K resolution in real life. That's what we call as 4K Pro, which contains 4K resolution images from 4 professional use cases, including but not limited to these kind of data sets, like autonomous driving, general daily things, playing games, etc. And we manually make sure each of the questions strictly needs the 4K resolution to solve. For example, what is the next exit? And what is next to the black project? And what is the level number on the top left? As well as what is the RAM usage? And of course, there are lots of other scenarios where we need 4K resolution, but it's very hard to benchmark. For example, here we show this this texture, but it's very hard to show this, to ask this benchmark answer purely text. But at least on the benchmark we curated, we see scaling to 4K resolution makes much more improvement over 1.5K resolution. And the VILA-HD is much better than all the previous multimodal LLMs and is also faster than most of them. Select is the high-resolution patch selection ratio of the PS3 at test time. Token is the total number of visual tokens fed into the LLM under the maximum input resolution. So to summarize, here we share the takeaway. One is localized contrastive learning allows scaling pre-training to 4K resolution for free. And the second is this requires a co-design of data, model, and algorithm. Then PS3 scales better the models without high-resolution pre-training and also helps with efficiency while bottom-up or top-down patch selection. And then we need new benchmarks to really show the advantage of PS3 under 4K resolution. So the PS3 is very exciting, but we have to say it's just the first step. There are so many things, lots of limitations of the current models, and lots of exciting directions that I think are worth exploring in the future. And I would like to share some thoughts about these. For example, like for data, all the high-resolution data usually have rich details. And for example, the existing benchmark, you can see actually the data we have is not that high quality. Specifically, lots of them actually don't contain lots of details. And we also need better bounding boxes because of some of the boxes are around the regions with textures, but not a meaningful object, for example, here. And also the quality of the captions is still improvable. We can use auxiliary information to make it more accurate and detailed, and we can filter it to remove the hallucinations. And there are other limitations on the model and the training as well, which I won't go into details here, but if you're interested, you can find it into the paper. For the future directions, one thing I think would be quite interesting is how to extend this approach to other pre-training paradigms rather than just CLIP. Because I think the idea of localized encoding is pretty general and can be applied to different pre-training methods. To give a few examples, we can scale MAE to high resolution by first doing global reconstruction and then doing local reconstruction of some salient regions. We can also do this for DINO, where we just apply the DINO loss to both global views and the local views. We can also combine all these objectives together like what SigLIP did. But I think the intuition is pretty general. Another exciting direction is how to extend this to videos, because currently what PS3 does is removing redundant information in high-resolution images, and video is much more redundant. Here we could see there are a lot of duplicate in content over different frames. So the same idea should be more powerful for videos. By extending the spatial patch selection to spatial temporal patch selection, we will be able to scale vision pre-training to not only high-resolution images, but also high-resolution, high FPS, and long-form videos. Although I don't think vanillally extending this video can completely solve the redundancy problem in videos. For example, in this video, if your task is to figure out where the ball flies to, you can use this approach to select a tube that contains the trajectory of the ball. But there is still redundancy inside this cube. For example, we know the appearance of the ball won't change too much, and the trajectory of the ball before the goalkeeper touches it is mostly predictable. So if you've seen the first few frames, you probably don't need to see the frames in the middle frame because they are predictable. Therefore, if the model can learn which frames or which token don't contain any new information and can be predicted, it can just throw them away. That would be much more powerful. But unfortunately, we don't have annotations for this kind of token selection. And we probably need something like reinforcement learning to solve it. Because we need something that can tell us if this is useful and how this could be applied into these regions. And what could be even interesting is to see if doing this aggressive comparison can force the model to understand the word better. For example, if the model can predict the trajectory of the ball in the middle frames given the first 3 frames, it must need to know the physical law behind this. So doing the comparison won't just help with efficiency, but probably can make representations better as well. And the more aggressive it is, the better the presentation can be. So we could see that we don't need to see some of the captions. And regarding our questions, we can do much more detailed analysis. And the more aggressive compression usually can lead to better word knowledge. And this is something that we always keep thinking about, because this is a very important thing that we need in the future. Once we finish scaling up the model, also the data, everything, how even we have this data, how we make full use of these data resources. And that's the talk, all the content of today's talk. Thank you so much for your patience and time. Yeah, thank you.
Thank you, Boy, for the awesome presentation. Folks, do you have any queries or comments? Please feel free to ask Boy.
Boy, thank you very much, Boy, for being with us here today. We appreciate your efforts here to help us understand your work, and I would say that the work is actually quite interesting. I have a few questions, so while others are coming up with their questions, I just want to drop my questions here. So I actually have 3 questions. Are you with me, Dr. Boy?
Sorry?
Can you hear me?
Yes, I can hear you.
Okay, so I have 3 questions. While the others are coming up with their questions. So my first question is, I observed that you, for the work, both for the S2, for PS3, and VILA-HD, you worked mostly with vision transformers. So I was curious to know if you made use, if you talk about experimenting with convolutional neural networks at some point. If that makes sense.
Yes.
Yeah. So I was just curious. Did you and your team try to see if you could extrapolate this performance from vision transformers to convolutional neural networks? Did you make any attempt to try that out and see what you would come up with?
If I understand correctly, what you ask is that how we select a patch.
No, sorry. I don't know. Maybe I'm not really asking that well. My point is, we know that before vision transformers, we had convolutional neural networks. We had CNN.
Yes.
So I observed that in the work so far, S2, P3, VILA-HD, all of it was built on vision transformers as the backbone, right?
Mm-hmm.
Yeah. So I was just curious to see if we could replace the vision transformer backbone with convolutional neural networks and see if we get similar performance, comparable performance, because we know that there is usually this argument we have where um, sometimes you try to see if you can go with vision transformers or you go with convolutional neural networks for vision related tasks. So I was just curious to see if you did any experiments, any ablative works in that regard.
Yeah. Yeah. I think this is that's a very good idea, but I didn't have the chance to chat up to try this. We didn't
Oh,
try it,
okay.
but I think it's tryable. Yeah, that's a very great idea.
Okay. The reason why I was just asking was because I'm aware that a lot of frameworks, especially PyTorch, they have very efficient kernels for convolution. And I think that if convolution operations can be useful for this work as well, then it would also spur further research into improving this kernel some more, like the same way flash attention came up. Flash attention was essentially an improvement on the vanilla attention mechanism because everyone liked attention and it was doing very well. So I think that if CNNs can perform very well on this task, it might even lead to more improvement in their design if you get what I'm trying to say. But thank you very much for your thoughts on that. So that was my first question. And then my second question is the um, the evaluation data set, right, your benchmark data set and 4K Pro. I'm curious to know how many images does it contain? How long did it take to curate the data set? And then what was the curation process like?
Uh, so what do you mean by the manipulation?
No, I mean, sorry, the benchmark data set. Can you
Yeah.
hear me?
Yes.
Yeah, yeah. So I know that the benchmark data set, which is 4K Pro, I know
Mm-hmm.
that the data set was benchmarked, it was curated by your team. So I'm
Mm-hmm.
just curious, how long did it take to curate that data set? How many images does it contain? What was the process like? I'm just curious to know.
I think we just used a few days. It's just hundreds of data set. And we already open. We release it. So yeah, I think all the things are open source and publicly available. Yeah.
Okay, thank you very much. I will check it out. I was just curious to know the process by which you were able to create it. Did you guys have to like take the pictures yourselves, or did you have to do a lot of internet search to find the high resolution images you wanted?
Yeah.
I was just curious. Nothing much.
Yeah. We basically utilize the internet search.
Okay. No, okay. Okay. Thank you very much. Then
No.
the, yeah, yeah. The last question that I have here is for your patch selection algorithm, because you came up with an algorithm to optimize for high resolution patch selection. Um, when you were discussing that algorithm, you mentioned top down and bottom up patch selection. Could you just expatiate a little bit on that?
So your question is when I do the patch selection?
Yeah. So you earlier you had talked about the patch selection process and how you do some top down and bottom up part selection. I don't really understand what you meant by that. I would appreciate a bit of clarity there.
Also, basically, we utilize the saliency, like we use DINO feature to find the saliency, and then we use that to crop the saliency salient region.
Okay. Thank you very much. I have a bit of a better understanding now. Mayank, I'm still expecting questions from you. Yeah.
Yeah. Boy, can you see the chart? And Max had a query in that chat. Max, if you can unmute and ask your query, or
Hello, Max, are you there? Max, are you there?
Max is there, but I don't
I
think
don't
so.
think
Yeah.
I don't think Max is on the meeting anymore. I think he
He doesn't
okay,
have a
he's here.
mic right now. Yeah.
Okay,
Okay.
yeah, I saw the question. So basically, yeah, we have done this yet. I think this is a very open question, and like the most similar way is that we can extract the redundant in content between patches between each frame, and then we can reduce looking at those duplicate content. That's some basic idea that we are considering about. But for the practical results, we don't have yet. But I feel like regarding video, the difference between video and the image, the content, the content duplication is much more serious. Redundancy is much more serious. So we believe this will be something that would be very useful to tackle this problem.
So, Max, I hope you got the answer there. Yeah. I just want to chime something in a bit quick. For the video problem, for applying this techniques to video, I think perhaps this is one of those areas where an event camera might come in useful, because event cameras are usually better for tracking the things that are changing in your field of view, in your field of perception. So maybe an event camera would probably be a very good idea to use something like this. I don't know, Dr. Boy, what do you think on that? Hello, Dr. Boy, are you there?
Yeah.
Okay. So, Max, did you get your answer? Are you satisfied with your answer? Are you good? Basically.
Yeah, I think so. He is.
Okay.
Vatsal, you can go ahead.
Okay.
Yeah, like my question is regarding VILA-HD. Like as you told that it sort of finds the local reason regarding the query. So if we get a query which uh, like the query is ambiguous and the model is not able to find a particular region, or like the query is related to the whole image that we cannot answer based on a particular localized region. So like how will the model behave in such conditions? Yeah.
Yeah, that's a good question. So basically, you can see we do not only input the patches, we also input a low resolution image into the model to give a context of the whole image. So we select the local patches to get the information, but as meanwhile we also provide the context, the content of the image to let it be aware of the context.
Yeah. Any more queries, folks? Benedict, do you have anything to comment or say regarding this, or we can end the presentation?
I don't really have anything else to say. I don't have anything else to say. It was a very nice session. Thank you very much, Dr. Boy, for being here with us. We really appreciate your presence.
Thank you very much for
Um,
the invitation. Yeah.